I am Sangjin Choi from KAIST, and in this talk, I will present EnvPipe, a performance-preserving DNN training framework for saving energy. This work is done with collaboration with KAIST, Ajou University, and UNIST. I want to start with something really important, climate change. Climate change is a serious problem caused by carbon emissions, and data centers are part of this issue, making up around 3% of global carbon emissions. Training and inference of large language models consume a significant amount of energy, and this leads to a significant amount of carbon emissions. For instance, training GPT-3 consumes enough energy to power approximately 44,000 US households for a single day. With the rapid expansion of AI, it's crucial for data center providers to actively seek ways to shrink their carbon footprint and make AI more sustainable. Let's explore previous approaches that have aimed to save energy in DNN training. Common methods use GPU dynamic voltage and frequency scaling, which seeks to find the optimal streaming multiprocessor frequency or memory frequency. Streaming multiprocessors, which I will now refer to as SMs, are small processing units responsible for executing thousands of threads in parallel in the GPU. By default, the SM frequency of a GPU is maximum, and we can reduce the SM frequency. By reducing the SM frequency, energy saving can be achieved with a trade-off in performance. Now let's learn more about GPU DVFS. We trained a small-size Megatron model using a single V100 GPU while varying the SM frequency. The x-axis represents SM frequency, and the y-axis represents throughput. As expected, the throughput shows a linear relationship with frequency. From the default maximum frequency, gradually decreasing the SM frequency decreases throughput. However, the energy consumption behaves differently. Initially, reducing the SM frequency from default maximum frequency results in energy savings. However, beyond a certain point in the middle, this trend reverses. The prolonged training time at lower SM frequencies leads to an increase in overall energy consumption. If the execution time increases at a faster rate than the decrease of the current power usage, the overall energy consumption increases. At the minimum point on the energy value curve, energy saving is maximized with a performance degradation of about 20%. Prior work focused on navigating the energy performance trade-off. However, sacrificing performance or accuracy in DNN training to save energy is a significant problem. For performance, it is difficult to determine an acceptable range of performance degradation for long-running jobs. Even a small percentage decrease in performance can result in a substantial increase in the absolute training time. Also, since the final training goal for ML practitioners is accuracy, it is important to save energy without degrading any performance or accuracy. The inevitable nature of bubbles in pipeline parallelism is an opportunity to solve this problem. For large models that cannot fit in a single GPU, pipeline parallelism is an efficient technique to train on multiple GPUs. The model is vertically partitioned as evenly as possible to each GPU as pipeline stages. Next, it splits the input mini-batch into multiple micro-batches and pipelines execution. The overall flow of pipeline parallelism looks like this figure. The blue box represents the forward pass, and the green box represents the backward pass. The number in the boxes represents the micro-batch ID. From GPU 1 to GPU 4, the pipeline unit executes the forward pass and sends activation. From GPU 4 to GPU 1, the pipeline executes the backward pass and sends gradients. However, because of the strict wait update semantics, wait update happens at every step and introduces pipeline bubbles. The gray bubbles are idle time in the pipeline, which reduces the training throughput. There are multiple ways to schedule the pipeline, and 1F1B is the most representative scheduling method. The 1F1B scheduling method tries to schedule the forward pass and the backward pass alternatively. Let's zoom in 1F1B scheduling method to see how we can use these bubbles. The right bar represents the SM frequency of GPU 3. What happens when we decrease the SM frequency of GPU 3? The forward pipeline unit 2 will stretch, and energy consumption of GPU 3 will decrease. However, there is no overall performance degradation since the prolonged time of FP2 was already consumed by bubbles. We can leverage pipeline bubbles to save energy without performance degradation. However, there are some challenges. First, not all bubbles are usable. Let's consider another pipeline scheduling method, gpipe. Unlike the 1F1B scheduling method, gpipe does not alternatively schedule the forward pass and the backward pass. It initially schedules all the forward pass and later schedules all the backward pass. What happens when we decrease the SM frequency of GPU 3? The FP4 on GPU 3 will stretch, but because this pipeline unit should send activation to the next GPU, the start time of FP4 on GPU 4 delays. This leads to performance degradation. We can conclude that these bubbles in gpipe scheduling method are unusable. We need to carefully identify usable and unusable bubbles. Secondly, there may be not enough usable bubbles. Stretching over the size of usable bubbles can degrade performance. The critical path, represented as red boxes, determines the end-to-end execution time of the pipeline, and it should be preserved. We should leverage bubbles just the right amount to avoid performance degradation. Note that the critical path looks like an envelope. Now, I will present the goals of this work. Firstly, energy saving should be maximized. We should leverage as many pipeline bubbles as possible to maximize energy saving. Secondly, there should be no accuracy degradation. We should not modify user-provided hyperparameters and preserve the original statistical efficiency. Thirdly, performance degradation should be minimized. We should keep the performance degradation to near zero for ML practitioners to use our framework. With these goals, I present EnvPipe, a performance-preserving DNN training framework for saving energy. EnvPipe is implemented as a library based on PyTorch. There are three main components: the profiler, the scheduler, and the frequency planner. From the user-provided DNN model and hyperparameters, these three components execute in order and generates a performance-preserving, energy-saving plan. The profiler profiles the performance energy trend for each pipeline stage. The scheduler schedules the pipeline units to maximize energy saving. And the frequency planner reconfigures to minimize performance degradation. The engine executes the performance-preserving, energy-saving plan with the hardware controller that controls the SM frequency of the GPU. I will now explain each component in the following order. First, the profiler. The energy consumption shows a value trend according to SM frequency, and the trend depends on the GPU hardware and batch size. It also depends on how the model is partitioned to each stage. Thus, the online profiler profiles each pipeline stage to obtain the performance energy trend. Our online profiling scheme currently profiles 5 steps per frequency, starting from the maximum frequency and gradually decreasing until the energy consumption approaches the minimum point in the energy valley curve. This process includes approximately 100 profiling steps, which is negligible compared to the overall training steps. When the profiling ends, EnvPipe continues the training process from the weight version trained in the profiling step. Note that since the SM frequency cannot be decreased farther below than the minimum point, there is a maximum stretch limit, which is about 20% in our settings. Now, I will explain the scheduler of EnvPipe. Scheduling the pipeline units determines the amount of usable bubbles, so careful scheduling is required to maximize usable bubbles. There are 2 questions to solve to design our scheduler. First, how can we effectively identify usable bubbles? Before we maximize the amount of usable bubbles, we first need to identify them. Next, how can we maximize the utilization of usable bubbles? We have to make best out of bubbles. To solve the first question of identifying usable bubbles, let's zoom in. What happens when we try to use bubbles after the critical path? Let's stretch BP4 in GPU3 to use the bubbles after it. When we try to use the bubbles after the critical path, the units on the critical path delays, leading to performance degradation. This is because the pipeline units on the critical path determines the end-to-end execution time of the pipeline. We can conclude that bubbles after critical paths are unusable. However, bubbles after non-performance critical paths are usable. This is because stretching pipeline units on the non-performance critical path does not affect the overall execution time. We can conclude that usable bubbles are after non-performance critical paths, and we need to stretch pipeline units on the non-performance critical paths. Now let's solve the second question of maximizing utilization of usable bubbles. Since we concluded that we need to stretch the pipeline units that are on the non-performance critical paths, we need to stretch all units inside the outer envelope with just the critical path. Let's first stretch the FP units at the front. Stretching the FP units at the front is free. We can save energy at no performance degradation. This is because the data dependency is far. FP2 on GPU3 needs to send activation to FP2 on GPU4, but there is enough slack time to stretch the unit. Now, let's stretch the FP and BP units at the back inside the envelope. Stretching these units comes at a cost of performance degradation. The critical path changed, and it is now not the outer envelope. There are two reasons for the performance degradation. First, there is immediate dependency between units on GPU3 and GPU4. Stretching these units on GPU3 delays the units on the envelope. We need to change the immediate dependency to far dependency with units on the envelope as much as possible to make best out of bubbles. Secondly, there is an uneven distribution of usable bubbles. There are lots of backward computation at the end, but not enough usable bubbles to utilize. Meanwhile, there are too much wasted bubbles at the front. We need to distribute usable bubbles to maximize utilization of bubbles. From these insights, we designed our scheduler. First, we initialized with 1F1B scheduling. Among existing pipeline scheduling methods, we found that 1F1B has the fewest units on the performance critical path. Next, we reschedule FP units to the front. By rescheduling FP units to the front, we changed the immediate dependency to far dependency and distributed usable bubbles to make best out of bubbles. Rescheduling FP units to the front does not affect training since all the data dependency is in the same order as before. Only the distance of data dependency becomes farther. Based on the generated scheduling plan, we stretched all pipeline units inside the outer envelope to maximize energy saving. However, stretching all pipeline units inside the envelope degrades performance. We can conclude that naively stretching all pipeline units inside the envelope degrades performance. Frequency planner comes to rescue. Since naively stretching all pipeline units inside the envelope leads to performance degradation, the SM frequency should be reconfigured on some pipeline units to minimize performance degradation. From the maximum default frequency, we stretched all pipeline units inside the envelope to the minimum point in the energy valley curve. And we should reconfigure the frequency on the change critical path to minimize performance degradation. But how much reconfiguration is needed? The critical path should be the outer envelope to minimize performance degradation. However, increasing SM frequency too much will reduce energy saving. Our first goal is to maximize energy saving. Thus, we should reconfigure just the right amount to achieve our goals. To achieve our design goals, our frequency planner runs an iterative algorithm. Initially, based on the scheduling decision, the planner stretches the pipeline units inside the envelope by setting the SM frequency to the minimum point on the energy valley curve. Next, it executes a single pipeline step, finds the changed critical path, and reconfigures the SM frequency on the critical path in small steps. It repeats the find and reconfigure steps iteratively to reconfigure the SM frequency just the right amount. The algorithm terminates when the critical path becomes the outer envelope. Since the algorithm repeats the finding and reconfiguring the critical path, we need an effective method to identify the critical path. Since the critical path decides the end-to-end execution time of the pipeline, the last unit, BP8 on GPU 1, will always be the last unit on the critical path. To identify the critical path, we should find out which pipeline unit is delaying the units on the critical path. Which pipeline unit is delaying the start time of the last unit? The forward path, FP7 in the same stage, is delaying the start time of BP8. Thus, we extend the critical path to the same stage. Let's look into another case. The yellow FP7 got reconfigured and the stretch is shortened. Which pipeline unit is delaying the last unit? BP8 on GPU 2 is delaying the start time of the last pipeline unit. Thus, the critical path extends to the next stage. From the back of the pipeline, the algorithm incrementally builds a critical path using this insight. The algorithm ends when it encounters the first forward unit, FP1, in the first stage. Now, since we found the critical path, we reconfigure the pipeline units on the critical path. It repeats the find and reconfigure steps iteratively to reconfigure the SM frequency just the right amount. Finally, the algorithm terminates when the critical path is the outer envelope. This ensures that the performance critical path is the same as that of without using EnvPipe, while our algorithm stretches as many pipeline units as possible on the non-performance critical path. I will summarize the overall workflow of EnvPipe. First, the profiler profiles the performance energy trend for each pipeline stage. Next, the scheduler schedules pipeline units to maximize energy saving. And finally, the frequency planner reconfigures frequency to minimize performance degradation. Our evaluations focus on confirming our goals, specifically for maximizing energy saving and minimizing performance degradation. We first experimented on a single node cloud instance with 4 V100 GPUs. We compared EnvPipe with baseline, which runs all GPUs with maximum frequency. We trained with the following models with the following hyperparameters. Performance for all experiment is measured by averaging the throughput of 30 training iterations after warm-up, and energy consumption is measured using the NVML library provided by NVIDIA during the 30 training iterations. The left figure represents the throughput comparison with baseline and EnvPipe. For all models, the performance degradation of EnvPipe is less than 1% compared to baseline. This confirms our near-zero performance degradation goal. The right figure shows the energy consumption comparison. The energy consumption is normalized to baseline, which consumes maximum energy with maximum default frequency. For all models, EnvPipe saves energy significantly with up to 25%. This confirms our maximum energy saving goal. Next, we experimented with 2 cloud instances, each with 8 V100 GPUs, so it has a total of 16 GPUs. For multi-node experiments, we trained a Megatron model with various possible configurations of data and pipeline parallelism. Achieving efficient memory utilization can be challenging when relying solely on data parallelism. Due to memory constraints, training could not be completed for the 2 scenarios relying mostly on data parallelism. Similar to the single node evaluation, the performance degradation of EnvPipe is less than 1% compared to baseline. EnvPipe saved energy significantly with up to 28%. There are lots of other interesting experiments in our paper. Please understand that due to time constraints, I focused only on the major experiments. I will now conclude my talk. EnvPipe is a DNN training framework that saves energy with no accuracy and performance degradation by leveraging bubbles and pipeline parallelism. To achieve these goals, we propose a fine-grained online profiler, a scheduler to make best out of bubbles, and a frequency planner to minimize performance degradation. EnvPipe can save energy up to 28% with less than 1% of performance degradation. Thank you for listening to my talk. If you have any questions, I will be more than happy to answer.